Right. So in this project, we have basically three challenges. One is to understand what kind of gesture would be suitable for user to express music that they want to listen to, and how we could track those gestures using a phone. Then a second challenge is how to extract gesture from the musical gesture, melodic gesture, and so on, automatically from audio recordings. And then the idea was so to develop an app that would be able to, you can query by moving the phone to perform a kind of gesture, and you want to get a piece of music that contains that particular gesture. And so the one challenge here is to be able to offer a piece of music that will correspond as closely as possible to the gesture, and also to make this quite fast. Right, so I will cover the three different aspects. First one about gesture strategies. So we can think about different type of musical dimensions that could be expressed using gestures. Pitch is one of the most natural way, like a pitch curve, a pitch height. Then we could also indicate the position of each note, if we like. We could indicate the dynamics of each note. We could then indicate metrical structure per session. And then it could get even more subtle, so maybe we want to express that the melody is composed of a cyclic repetition of a pattern, so we would make some kind of cycles, or then we can express semantic aspects, opening, closure, or emotions, so this could get very tricky, very interesting, but difficult to model. But then this parallel problem is what type of gesture could be mapped to these different musical aspects. The simplest one, most natural one also maybe, I mean, at least for our project we found it very natural, is just this up and down, so you move the phone up and down. It could be related to pitch height, so this looks like a theremin. You could also indicate notes position by making some kind of gesture like this. This looks like natural because this is the way you would play on a percussive, some vibraphone or percussions. And then, yes, you could, dynamics per session, also per session you could express like this with up and down. Then another type of gesture would be to move the phone in other ways. So I was trying, because this up and down was what I showed already in the last workshop, and we mapped to pitch, but I was trying to consider other type of gesture. And so I implemented some version of the model where you can move in different ways, in different dimensions. So like this, for instance, like this, right? But the problem is very complex, because then we need to know what are the dimensions, and where is the center of this space. So actually it's too complex. So I think for this version of the SoundTracer project, it's better to just use up and down, because else it's really too tricky. Yes. Right, so that's the idea for here. And we will see, here we will consider not only pitch, but also onset location. And it will be easy also to add dynamics, expression of dynamics on this. Right. So now about how to find those musical gestures from audio recordings. So we were using this folk music catalogue, a part of it containing pieces from the 60s, 70s, if I'm right. And there is 343 recordings, each of 1 or 2 hours. It's like a mixtape where you have a succession of songs or tunes with the musician presenting the song at the beginning of each tune. So you see here, let's say each line is one recording, and you have the person, the musician, first presenting the tune, and then playing, either singing or playing fiddle. Many of the examples is fiddle or songs, but there might be other instruments as well. How to get the exact those tunes precisely? We want to get the excerpts as a audio file for each tune separately. Thankfully, there is also metadata that give information about each tune. So you get the title, the genre, the region where it has been taken from, which instrument, who's performing, which date was it performed. And there is a kind of approximate location, temporal location of the recording of the tune in each recording. So it will say one particular recording starts around that time in the recording and ends around that time. But it's approximate. So because the idea is ready to extract, we have maybe it was tens of thousands of tunes in this 343 recording. We want to automate all of this. So we need to be able to detect those exact location of each tune. So let's look at an example maybe to show. So I will play around one of the beginning of this tune. We will hear the end of the previous tune, then the musician introducing the next tune, and so on. So let's listen to this. O Jesu Christe boll. Then usually there is some silence, which is helpful for the segmentation.
Dagen viker og går bort, sungen av Harald Hope.
And the next
Dagen viker og går bort.
So how could we detect the beginning of the next song? We can simply first just look at the evolution of the dynamic of the audio recording. So you see here the envelope of the audio signal. And already here we can see an important description that helps for the segmentation. So discrimination is that usually when you sing long syllables, whereas when you talk, it's quite very short. And so that's one parameter that's very helpful to do this. So we can just say, after these small parts, there is a little silence, and then longer parts, so we can start segmentation here. And actually, if you let's listen to this curve by listening to the noise that is modulated by the curve. So I play this, I hope it's this is silence. You perceive here this is talking. No, okay, thank you. It's quite intuitive. We can hear the talking just by hearing this noise that is modulated by dynamics, but it's not sufficient. So there is, in some case, where it's not that short that it's not use enough information to discriminate. So then we can extract the pitch. So I will present this in next slides, how to extract the pitch from the voice or the violin, for instance. And then there is another parameter that when you sing, usually you will have a constant frequency that will modulate a little, but not that much compared to voice, where there is a lot of inflection of the frequencies. So we use this also a parameter for the segmentation. And this is sufficient for this type of problem to make this type of segmentation. Right. And the next problem is also, it could be nice to detect what kind of instrument is played for each excerpt. For the moment, due to the complexity of the questions and the timescale of the project, I thought because we have the information already in the metadata, it's good to just use the metadata. But there are lots of music information retrieval technologies available also for detection of instruments. And here we could use, for instance, to discriminate between singing and fiddle. Well, fiddle is kind of polyphonic. Always, maybe it's not always the case. That's one parameter, but we can use the timbre of the sound, different description of the timbre of the sound, and so on, of the attacks for the discrimination. And for instance, there was a presentation in last workshop by Mattia Marolt, who presented research about this discrimination. Okay, so so we will focus on extraction of pitch, onsets, dynamics. From voice, it's quite simple to extract the pitch because it's just a monody. So technically, you can just compute some kind of autocorrelation function, and you get this type of curve showing the evolution over time of the frequency. And then you would like to be able to detect each note that is played, the beginning and the end of each note. So there are different algorithms that could be used. I was developing previously an algorithm that was more adapted for instruments, violin instruments in particular. And it turns out that Christian Nimuen has developed a nice algorithm for voice, and it was used in particular for this Norwegian folk music. So this is used for this particular case, integrated into the Miller toolbox that we are developing. And basically, the algorithm will detect the change of pitch. You see you have abrupt changes, and it will detect when there is this abrupt transition of frequencies. Right. Right. So now about Hardanger fiddle music. It's a more complex problem. We want to find the different pitches, start and end of each note, as the same as for voice. It's a difficult problem for polyphony. Even in the state of the art in music information retrieval research, for instance, let's say there would be 70% of accuracy. Even for kind of simple music material with just 5 or 6 instruments, so on. Many of the current methods, most of the methods are based on either they have a kind of series of template of audio samples. There is audio samples for each possible notes for different instruments, and they use this as a kind of way of mapping the recordings with those samples. Other methods would use also statistical modeling of the musical style, so that they will know some kind of expectation. If there is this note that is played, they expect that there should be this kind of note, not the other one. This could be useful, but what about any kind of music that is not modeled? We don't have yet any stylistic model. And I guess for Norwegian Hardanger music, we can't expect to use the same model than for other culture. So the idea is to try to, directly from the signal, to be able to detect those notes without any prior knowledge about what type of style and what kind of instruments and so on. And the hypothesis that I have is possible to get something, quite a good transcription, and it seems to now work quite well. And we'll show you. So it starts from a spectrogram like this. I will show more in detail. So can we? Oh, was it? Oh, since when is it like this? Did it just?
You can try plugging
Was it for a long time? Yes?
Guds god.
Okay. Strange. So. Yeah. I will show more in detail, but you see the spectral representation with time from left to right and the frequencies from bottom to up. And for each note, the problem is that you see for each note there is a kind of line, like a piano roll representation. You see a line for each note, but you get also a line for each harmonics of each fundamental. So I will show examples precisely in the next slide. But for instance, here, this note, you have harmonics here and here and here. So it's getting very blurry and mixed, and it's difficult to see where are the actual notes. Yes, and what we get at the end of this algorithm that I have been developing recently, I'm still working on it, improving it. We get something that now looks like a piano roll representation. It's the same thing, the time from left to right, the pitch from bottom to up. And we have each note as a line, a black line. Detection of the beginning of each note showed by some kind of red cross. And we can see in detail, I could zoom in, but there is representation of the vibrato of each note that is shown, tracked quite precisely. And yeah, we get the notes like this. It's quite clear, but there is still sometimes missing notes or notes that should not be there that are there. So false positive, false negative. But it's a work in progress, and it seems that I could still improve that. And now I can explain a little how this works. Yeah, I can play first this example. Let's play it, so there should be sound. Is there any sound playing? No. As this was the bad contact. Yes, we will play again later. So let's look. I will explain a little more in detail. The same. Zoom in. And let's look at some of the first notes in this excerpt. For instance, you have a very short B at the beginning, very short. We don't really hear it much, but it's here. And it's shown. So there is just a small B. And it's here. Yes. So you have the fundamental of B here and just one harmonic of B here. Then you have this E here. And so you see here the series. You see already there's some kind of mixture because let's say the third partial of E is exactly the same level than the second partial of B, because it's a fifth above E. B is a fifth above E. So, so you see now it's getting confused, so we have to be able to discriminate, separate these different partials. And more difficult, for instance, here is that there is the note at the octave above that is played also. And here it's played a little after the lower E, but sometimes it could happen at the same time. And now it's just mixed, so we can't see clearly which partial is related to lower or higher E. And especially if you have this series of partial, can you decide is there or is there not a hierarchy there in the signal or not? This is the difficult question. And for instance, you have the same problem later. Now we have the B, very low B here. Yeah. And this F sharp that is part of the melody that starts here is just like the third partial of B, so it's also a kind of sub-series of the series of B. So we have to be able to detect this. So usually in the state-of-the-art of models for audio transcription, pitch extraction like this, they will try for each successive time, let's say, instant, you have a time frame for each time frame. You try for each time frame to find all the series of harmonics and decide which are the notes. And the decision is made for each frame. And then you try to track to follow properly to track those partials to make notes, to decide that there is a beginning and end of notes. The problem is that it's difficult for each frame, separate frame, to make the decision. And actually, it's quite impossible. I made some experiment where I tried to listen to a short frame for a particular excerpt. Sometimes I couldn't distinguish. But now, if I listen to the passage before the context before, then I could say, yeah, of course, it's because there is something arriving. So there is this dynamic evolution of the harmonics that plays an important role. And this is what I have integrated in the approach. Yes, so... And also we could say how to get very good time and frequency resolution. Usually with the spectrogram, you can't get both good time resolution and good frequency resolution for mathematical reason. But here we take very short time frame to have a very good time resolution. And then in order to have a very good frequency resolution, the idea is we take the partials, this series of harmonics, help us to have a very good frequency resolution. But this is also a common method that can be integrated here. And finally, there is something just for your interest to explain a little about those techniques. It's important to know that it's not just about mathematical description of the sound, but we have to consider some kind of cognitive aspects or perceptual aspects. And for instance, here, we should not just use the spectrogram itself, we should add some aspect related to perception. Why? Because the harmonics are not so easy. We can't see clearly in this representation some of the harmonics that play such an important role. But actually, the outer shape of our ear plays a role of filtering that will make more focus on the frequencies around 2,000, 4,000 hertz. So if I model this aspect, we will see the transformation here. You see, now we see more clearly that we have these harmonics that play a very important role. It's interesting to see that actually in what's happening in real life, those volume doesn't make such sound. It's just our perception of the sound that make us detect those notes. But it's not the end of the story. We didn't get a melodic curve. So far we get a nice transcription, but it's kind of polyphonic, and we wanted to have something like a gesture or something, like a monody. Actually, this example is quite complex because this is the way I perceive the melodic gesture, but I guess maybe you will not necessarily perceive it the same way. So if I play you again this piece. So there is this melody on the top register, but at the beginning, for instance, because the melody doesn't start really first, there is a long note. We don't really hear it that much, but we hear kind of accompaniment motif that plays quite an important role at the beginning. And for me, I perceive like this. So there is this lower motif first, and then the higher phrase, and so on. So there is some kind of maybe subjectivity. But so let's just try to make some kind of phrase out of this music that could be used for the project. So I'm currently still working on this aspect, but we can use simple representation, for instance, the heuristic space and distance between pitch. And have a preference for higher register. So usually if you have a lot of notes, you will perceive the higher line as a melodic line. But here, if in the higher register it stopped, there is no activity anymore for some time, just even a few seconds, or if there is just a kind of drone note, which is quite characteristic in Hardanger music, then we can just focus on another melodic line in another register. So yes, this is how I'm working on that. And yeah, so this different algorithms I make them available in a toolbox that is available for free, but using this MATLAB environment. So you can analyze audio recordings and getting different aspects of the music, including pitch extraction. And the new toolbox that I've made recently is that it's not just analysis of audio recordings, but also analysis of score representation. And for instance, those particular aspects here, you see, for the extraction of the melodic line from this pitch transcription, this is a part that is related to the symbolic representation, analysis of the symbolic representation, which is included into this mining suite. I should add that this was for pitch, but now that we get the notes transcription, we get also the onset location of each note that could be used for this estimation of rhythm, rhythmical aspects. And also we have a description of the dynamics, information about dynamics, because for each curve we get also an indication of the intensity of the note at the successive time. But then for further work, we could work on pulsation, that is quite very complex for Hardanger music. Right. Now we can focus on the problem of this retrieval aspect. So we got I will show in the demo the interface how to express the gesture. Then we get this transcription from the recordings, and now how to get the proper recording based on the gesture that you have traced. So first, we have to see how we can compare the gesture that you play with the phone and let's say the melodic phrase that is characteristic of a given piece of music. I should say also here that so far we focus on the beginning of each song, like the incipit song as a characteristic melodic phrase that will be used for the comparison with the gesture. We have to simplify as much as possible, can't consider everything. And so to compare the curve with a melodic line, one question will be, for instance, about pitch. We could express the pitch height in an absolute way, saying, okay, at this level, this is F sharp, this is E sharp, D sharp, and so on. But this will be very tricky. It's more convenient to indicate pitch intervals. But again, if we say this distance is like a major third, it will be also quite complex. So let's just consider a contour. So if you, what we look is you will make ascending and descending contour. And for instance here, for this particular melodic phrase, this will be maybe a good contour description with descending, ascending here, and descending again. And the other aspect is you could just indicate notes. So in this case, you don't represent the pitch itself of the note. You just make some kind of percussive gesture. And for the time description, you could either represent each note's duration in a kind of absolute way, in physical time, in seconds, or you could express in rhythmical values. I mean that you could, for instance, make a gesture where you have a kind of rhythmical pattern, and maybe you don't expect the gesture from the music recording to be on the same tempo. It could be on another tempo, and you want just to keep the same rhythmical values. But here also we can. This is one possible factor of comparison between gesture and gesture from the phone and gesture in the recordings is that we can say if the music that is found has the same tempo, similar tempo, is a good match. So if we add this tempo factor into account, then we can just say, let's just look at durations and just try to find music that has the same note duration that's the one that you played with your phone. And it's also possible to describe pitch without temporal description. And finally, what I just already mentioned is that there is this two way. You could just indicate contour, ascending, descending, or you could also represent the actual notes. For instance, in this case, this you just show the evolution of the contour, but it's possible also, I will show in the demo, that in the new version, you can express the successive note in a given contour representation. So you will see that. Right, so now let's say you want to compare. You have a lot of possible gesture in the catalog, and you have played a particular gesture with the phone. And as I mentioned, there are these three possible types of gesture. So it could be either just ascending, descending, or you could specify at some point there is a new note here in that contour. Or you could also specify, yes, this is this adapter. Okay. And so, again, this just ascending, descending. This is ascending, and then you say, here I want a new note at that position, and continue ascending contour. And this is, at some point, you indicate there is a note here, but without specifying which pitch height. In the first version of SoundTracer that I showed in the previous workshop, we were just looking at this ascending, descending, and to compare your gesture with each possible gesture in the catalog, we do this dynamic time warping. So I can explain in a simple example. So you have, this is your contour here. This is what you have, your gesture. It was ascending, descending, and ascending here. So the ascending phase of your gesture is similar to the ascending phase of that particular gesture in the catalog. So you start drawing a line here, like this. This contour is a little longer than the contour that you have actually drawn with the phone, so there is a little penalty for the change of duration. But then the descending phase here is same here, so you continue tracing your path here. But here it's a reverse. Yeah, we have choice. Here we could skip that part, so that's like here, and continue the descending phase that was here. So that descending phase is continued, and compared to that one. And in the end, we can just skip that part. So this gives one possible way of matching these two gestures. But there could be other possible ways. For instance, you could say, actually, the gesture that I'm drawing starts here in the gesture from the catalog. So it's here. And it continues here. So it means that you compare this part with this part. So of course, the penalty will be higher. So sorry, it was this path here that I was showing. And you can see with this red line, if you sum up all this red line, you have a higher penalty. The idea is to compare all these possible paths and take the one with the least penalty. That will be the best match. Okay, so that was for the contour, if it's just ascending, descending contour. Then I have added this idea of you can specify on-set location or on particular notes. And the idea is just an addition here that, let's say here, you specify that you want a new note starting here. And the idea is that you have now a constraint saying that the change of note in your gesture should be at the same location that the change of note in the catalog, in the example from the catalog. So it means that there should be a crossing here at that point. So that gives an additional constraint. So this is to make sure that you have a duration of note that is the one you ask for. And then to add this idea that you can specify also particular notes just with pulsation, that leads to additional constraints or things like that. Right. So yes, it was like this. I will show a demo just after this. So it's the app has been developed for iPhone. It's available for a recent version of iPhone and iPad because it used a particular technology, ARKit, because we needed to get both the inertia to have a good description of the position of the phone. We need both inertia and video representation using the camera. And so this is using the ARKit here. So you will get a new version 0.3 early next week with the demo I showed here in the next slide. But the version 1.0 in 2 weeks, I hope to have finished this transcription, automated transcription, so that we could add more tunes. So in that prototype, for the moment, there is 50 tunes, but we are aiming to have more. And for future works that have to be considered, we could add more musical aspects such as magical gesture, musical ornamentation, and not taking just incipits at the beginning of the melody, but trying to find some kind of characteristic melody from the music based on motivic analysis. And consider other features, for instance, timbre features in the music, and more high-level description of gesture. And apply for other catalog of music, why not? Right, so maybe if you have questions, we can discuss, and then I can show the demo. Depends. Thank you.
All right, thanks. Could you say something about the music database you're using now? Is that locally on the phone, on the app, or are you looking up something?
Yeah, no, it's we have excerpts on the phone to simplify or so. But if we would like, we could try later to have a...
Yeah, because it would definitely be interesting also to be able to look up in the sort of entire database that would be here.
Yeah.
Yeah. Thanks.
I have a question about how CPU costly is these things if you want to, scale it up and run it on a large database?
That's a good question. I should make some tests further. So far it's quite instantaneous, but there is just these 50 songs, but now it's very fast. We have to check this, yeah. That's the worst case. If we have problems, we have to reduce capabilities of the mapping.
Thank you. I wonder, is it possible to integrate humming and this at the same time?
That would be very simple to do, actually. I guess we are planning to have voice transcription also implemented in the phone app, so we could actually combine the two.
But would this humming task be the same as the extraction from the record?
So you would like the humming to be the query, or the humming to be...
Or somehow to integrate. I suppose that people making gestures maybe were humming at the same time.
Okay, yes, why not? But then we have two curves, yes, we have to...
And perhaps they're not even equal, those curves.
Yes.
Okay, so perhaps we should look at the one.
If you were to include more, like a bigger catalog, is the idea to also download everything with the app into the phone, or would you be using maybe an internet, like
so
SoundCloud?
That's the thing, that to scale up to a big catalog, we will...
Shazam and those kind of things, where they have the database. So, like Shazam, the app that tracks sounds and finds the song. So something where you don't have to download everything into the phone. And if you were to expand the catalog, I mean.
We should do like this.
Thank you.
But it could be good also to have a kind of offline version if your phone is not connected, so to have a few samples or have a part of the catalog in the phone. But yeah.
Yeah, thank you. Just maybe a more technical question concerning the dynamic time warping, the matching. You calculate the penalty of the good fit or the not so good fit. But could it be possible to have, let's say, an output that ranks possible outputs from the best match to the worst match? Is that implemented?
To run? Yeah. You mean like showing several outputs? And,
because that's quite common in the MIR or MIREX, that you have this ranking of the goodness of fit, or whatever it's called, from the best and probabilities for this.
So you mean to show several...
that you get a list, so you can evaluate yourself by listening which one is closest to what you were looking for.
All right. And to collect this user...
You could collect it, but it could also be a useful tool when you are browsing a collection to see which one is closest to what you had in mind. Because you might not do the gesturing so well. You might actually hit a neighbor of what the system recommends.
Yeah, it's true. Actually... it would be good in the interface to have several gestures. Actually, it could be very simple to just make some kind of button that will slide between different gestures. You could check. So,
Hi. Is there any differentiation between the different recordings in the collection at all? Are they all sort of just grouped together as one large catalogue, or is there any sort of difference between where the tunes come from geographically or anything like that?
Yes. So
is there any connection between? Is there any possibility of connecting different gestures to different locations or different traditions of music or anything like that?
So, in the first part of your question, definitely the catalogue indicates a lot of information about different regions, performer. And this could be used as a way to do this type of musicological analysis of the catalogue too. Because now that we have the transcription, we can make interesting musicological analysis. Yes.
And just following up on that, because I think it's a very good idea, and I think you would probably make different type of gestures if it's a vocal recording or if it's a fiddle recording. So you could also consider the type of instrument and like maybe not pitch curve would be the best for all types of recordings. So you could segment by or make different groups by that as well.
Yeah. Mm-hmm. Yeah.
One more.
I wonder if this could be integrated with some kind of machine learning functions, so that if one person is doing a lot of things, the program or the machine could learn from fits and misfits in some ways.
Yeah, that could be nice, and it could be feasible. Because if we get different, for instance, we get different matches for a given query, and then the listener could make some kind of judgment, and we could use this judgment as a way to improve the mapping. Is it machine learning? Yes.
Is there any idea of a kind of a sparse representation of contour that would be kind of faster on a database level, but also perhaps useful for other kind of large databases for contour annotation?
What do you mean by sparse representation of contour?
Like, in the way that search catalogs can have minimal items for kind of faster and faster indexing. I wonder what are your thoughts about kind of contour indexing as a kind of maybe possible idea?
Yes. Is it you mean like this type of that we can get the catalog of different pieces of music based just on the ascending, descending contour? Yes, and it's true that now that we have this melodic contour gesture we could get this contour gesture for all these songs, tunes, and we could have an idea that for a given contour, like the beginning of a contour, we have hundreds of songs that have the same contour. Yes, and that we could make some kind of analysis of this. And
It just dawned on me that Meinhardt's book, his first book on motion capture and sound analysis, there is this kind of sparse coding of motion capture data. Isn't that so, Meinhardt? Where you have the binary right foot in front of the left foot and stuff like that, which is, if I misunderstood it, it's very compact, and it can give a kind of very coarse classification of postures and motion, if I'm not totally mistaken.
Yeah, similar things also exist for music with up-down repeat sequences, similar in nature, which can then easily be indexed. So have you tried out this up-down repeat sequences or so?
Sorry, up-down repeat?
Up-down repeat sequences for which so...
Good.
Only encoding that the contour is going up,
yes,
down,
that's what.
repeating, and so
yes.
it has been used for melody retrieval.
Yeah. So that's what I meant by. I should have said gross contour, up down. Yes, that's what I'm using for those. Yeah.
Very good. So I think we are eager to watch the demo now.
Okay. So let's see. So we start with simple gesture. So this contour, which is just tracking the up and down. And yeah, so it moves like this. But it's not synchronized or what? It's not synchronized, sorry. Oh, because I remember it was absolutely not. I made the export into QuickTime, and I guess this seems to be okay. I will try again from here. Maybe I edit the video, and maybe the sound was not. I lost synchronization. That seems better now. And you see for both gesture, you have a time tracker, show the correspondence between the two. We can see the transcription. So let's see if it gets more. That's it. So here, for instance, in this first videos is just with the voice, and then we will see also including Hardanger Fiddle music. Let's see what's there. Maybe. Yeah, so now we can also indicate notes on sets, and it will show with a blue line detect. So now it's used this as an additional constraint for duration. When you have red line, it means that it's skipping a part of your Oops.
store.
Let me see if I have then with percussive elements.
Hvor det blir godt og lande ved himmelens stille kyst, og ei med topp, hvor det blir godt og lande.
Let me just try to see percussive ones. Can get boring to look at it after a while, isn't it? It's still a little fun to use it, but look at the video, it's okay. This is getting tricky for the pitch transcription when he sings very fast like that. I'm not so singing style, sometimes it's like talking. Yeah, so this is percussive. You do like this, so you define onsets without indicating the pitch. So it's a red line instead of a blue line.
Jeg vet meg en søvn i Jesu navn.
And there are some bugs. I have to fix some bugs because we added these new features. Of course, it makes new bugs. Okay, and let's look at with Hardanger. Let's see if I just do it. Also, one thing to consider is, especially because there are not so many tunes, there is this kind of hub problem that sometimes it's always the same piece that is found. Okay, I think you got the idea, right? Yes, so maybe that's it about the demo. So, thanks.
Yeah, thank you very much, Olivier.
If you want to try, just use it during the break. You can try it.
We have a 15-minute break now. Some coffee there, and you can download it or try it here. Comment and coffee as well. And then minor this on right after the break.